Hello everyone, I'm sorry for the bad mic quality, but this is all I have for now, so I'm going to record it anyways. So this is a discussion I led yesterday at Mila at the Neural AI reading group, and I'm going to run you through my slides for that discussion right now. And the discussion actually went quite well. We had Blake and Joshua join us, and they did give us a very interesting perspective on the paper, and we had many back and forth, people pushing back on some of their ideas, and Joshua and Blake giving them good convincing reasons why this framework makes sense. So let's get into it. So this is a paper by Blake, Joshua, and many other cool authors, a deep learning framework for neuroscience. So this is the paper in one slide. This is what they're essentially arguing for. They say that focusing on high-level principles of objective functions, learning rules, and architectures will benefit neuroscience. And these are the key points in the paper. So they initially argue that traditional neuroscience is limiting, and then they argue why deep learning networks are useful models for the brain. And the most tractable way of understanding these deep networks is using high-level principles of objective functions, learning rules, and architectures. So they argue that the same would potentially help neuroscience. And they further talk about more practical suggestions on how we need to build models of the brain in light of this framework. So let's get into it. First, they argue that traditional neuroscience is limiting. So in the traditional or classical framework, people observe neural activity and then develop a story or theory of what individual neurons compute, and then they assemble all of this information to come up with a circuit level theory of how neurons compute. This works well to understand simple computations, but this process has not given us much success when we go into more complicated circuits like the neocortex or hippocampus. This is probably because the neocortex and the hippocampus have a very distributed representation, and to try to come up with a compact human story for each neuron might not be possible. And yeah, so that is the issue traditional neuroscience framework is facing. Researchers can't summarize what these neurons do in a compact human understandable manner. And then they go on to argue why deep learning is a useful model for the brain. And they start off mentioning this study where artificial neural networks are used to mimic representations and manipulate neural activity in the primate perceptual system. So this is work from DiCarlo's lab at MIT. What they essentially do is they train a convolutional neural network on natural images, and then they map each neuron in this convolutional network into a neural site on the primate brain. And once they do that, they try to excite one of these neurons in this convolutional network and find the image that maximizes that specific neuron. And then they feed that neuron directly to the primate, and it turns out that the neuron that you maximized here for, when you feed that image, the corresponding neural site glows. So this shows that deep learning is somewhat useful. With these kind of approaches, you can control which part of the brain you want to stimulate. And not only this, but there are many other studies where various neural and behavioral phenomena emerge when you train neural networks that you don't explicitly code in. For example, visual illusions, grid cells, and shape tuning. So one example of visual illusions is this. So the image on the left is a visual illusion for humans, and the image on the right is not. And so when you train a deep predictive coding model to predict to predict how the next frame would look like, and you train this model on natural images, and you test them on these visual illusions that it has never seen before, it is able to predict what kind of illusions humans have. And the same also happens in this case, where researchers at DeepMind train agents to solve tasks similar to what rats solve in mazes, and they realize that the artificial agents develop a coding of space which is similar to how rats code their environment. And some people counter argue, sure, ANNs use backprop, but that is not biologically plausible. But the paper argues that even though that is true previously, there are recent models which show promise that biologically plausible algorithms can approximate backprop. So it isn't as big as a hurdle as we previously thought. And another important consideration when we train AI and brain is the tasks that they are trained on. So AI set, defined by Jan LeCun and Yoshua Bengio back in 2007, is defined as set of tasks that animals and humans are good at. And deep learning is successful because of the focus on solving problems in the AI set, where we're trying to encode the right inductive biases for such tasks in the natural world. For example, image recognition, or say NLP. And when we do this, we get useful models for the brain when we are trying to solve deep learning on the same tasks. And so the researchers suspect that building artificial neural networks that consider brain sets, which define as the set of tasks a specific species is good at, or what it has evolved to do, might also help. Moving on. Then they start arguing that the most tractable way of understanding these deep networks is by using high-level principles of architectures, learning rules, and loss functions. So what do we mean by understand here? So let me define understand in the context of just this paper. So to understand something means that it needs to follow the following properties. Number one, it can be compressed into few rules. Number two, these rules must be able to convey a human-centric story of what is happening, as opposed to just pointing at raw computations. And it should be easy to build variations of it from these few rules. In short, we need compressibility, adaptability, and anthropomorphizability. So if we think about the term understand now in the context of a trained deep neural network, a trained deep neural network is essentially a computational graph with all the weights and connections from various neurons. So this does not satisfy the properties of understanding, because millions of parameters are in the network and it doesn't give a short, compact, human understandable story of what is happening. And you cannot also build variations, because if you train the network on task 1, say apples versus oranges, it is very hard to make it work on cats versus dogs unless you go back to the development principles and think from there. And the development principles satisfy the properties of understanding because architecture, learning rules, and objective functions are compact representations of what we understand about these networks. And once you have this, it is easy to build variations of them, variations of a neural network. And you can train it on whichever task you want when you're analyzing them from these principles. So, summary until now, traditional neuroscience is not working. Deep learning forms good models for the brain. To understand deep networks, we need to use high-level principles. So they argue that the same framework could potentially help neuroscience. But how do you build models under this framework? So The authors argue that when we build models for the brain, we need to check out on the following criteria. Number one, they need to solve similar tasks as the brains do. Number two, these architectures must be informed by anatomy and the learning rules must be informed by the plasticity knowledge, and they should be able to reproduce representations in the brain. So next, let's move on to specific guidelines on how to run experimental studies to figure out these high-level principles in the brain. So number one, empirical studies of learning rules. So the authors argue that when you're studying learning rules, a lot of previous people have studied synaptic plasticity, but they haven't focused on the problem of credit assignment. So they say more focus on the credit assignment would help. Some examples of these research, one of which I'll go into more detail, is apical dendrites, how apical dendrites or neuromodulators are involved in credit assignment. And they also talk about a study which uses changes in representations to infer plasticity from those observations, which they think is also promising. So to give you a more clear idea of what this actually looks like, let's look into a specific case of it. So this is an opinion piece from Blake and Tim Lillicrap at DeepMind. So what they essentially argue that okay, let me start with a little bit of neuro background before I go into the paper. So these are pyramidal neurons on the human neocortex, and this is the cell body. And what you see around them are the dendrites, so the dendrites close to the cell body are called the basal dendrites, and you also have connections from a different layer in the neocortex, which is where your apical dendrites are, and you have an axon going down. So here they argue that the information that you're getting from apical dendrites is feedback information, and they are probably giving you some kind of gradient signals. And they propose that instead of using a Hebbian style learning rule for strengthening or weakening your synapses, you can instead use a three-factor learning rule where the third factor is modulated by the feedback that you're getting. And they make a very good argument on how you're getting gradients through this feedback and how this might be helping in credit assignment. So they don't say anything for certain. They say that we need to run more experiments to verify that this is true, and they hypothesize this based on multiple lines of evidence, including single neuron recordings, biophysical simulations, and neuroanatomy. Next, they talk about the empirical studies of architecture. So they say we can identify architecture by continuing to run more experiments like we already do, and they specifically quote studies which are valuable in this respect. So they talk about mapping hierarchy of the brain and probing which parts of the deep neural network best reflects various brain areas. And they say this is not just a one-way thing. This would also involve optimizing the architecture of deep neural networks so that they provide a greater fit to the representation dynamics in the brain, which I found quite interesting. And they talk about a study that maps out projections of neural circuits with specific cell types, and they also say along the way we are going to make many surprising anatomical observations, and all of them should be incorporated into the architecture. Next, they talk about empirical studies of objective functions. So this is something that has been less explored in the literature, and this is one of the more controversial ideas. And they say that they talk about a few studies that find objective functions, and here are them. Number one, you can estimate the objective function by comparing neural activity observed experimentally with the neural activity of a trained artificial neural network, which is of course trained on the same task set. And you can use ideas of inverse reinforcement learning to figure out what the system is optimizing. And you can also find objective functions by looking for correlations between representational geometries of neural networks compared to brains. And that was mainly their paper. So the language they use is quite soft, and they also mention a lot of caveats, and here I quote some of the more interesting ones. They say that focus on high level principles doesn't mean that we move away from understanding the coding properties of individual neurons. They say that all of this information will be helpful to infer the high level principles. And they say this also doesn't mean that we ignore the dynamics of neural activity, and the dynamics can also help us infer high level principles. And they say it's not only about understanding high level principles, and high level principles can be used to guide the understanding of low level principles. And they also talk about okay, what was this? Comprehensive theory, might attention. Oh, okay. I did not frame this properly. I'm sorry, but what they essentially say is there may be something more than objective functions. Maybe all of the brain activity might not be explained by just objective functions, and they're saying they're just mentioning that it's not all objective functions, there might be something more to it. And they conclude saying that there is no guarantee that function of individual neurons can be compressed into human interpretable, articulable, human-centric story form. And artificial neural networks are understood by using development principles, and maybe neuroscience can also benefit the same. And they say ultimately people need both bottom-up and top-down frameworks to understand the brain better, and they say top-down framework could be guided well by insights from deep learning. And that is the end. Thank you very much. I hope you found this helpful.